Okay, folks, this is just a quick run through the second example we did in class for a friction type question. And in this question we had a 100 kilogram box on an inclined plane. So this box that we had in our question was 100 kgs, which we know if we multiply 100 by 10, which is force of gravity, we end up with a weight force of 1,000 newtons. And in this question we were given a frictional coefficient of 0.4, and we know that the angle of static friction, which is this one here, phi, is equal to tan minus 1 mu. So we end up with a angle of static friction of 21.8, okay, because we just go tan minus 1 of 0.4. Okay, that gives us that angle. Now that angle we know is living between the resultant of the frictional force, which is on the free body diagram here, and our reaction normal. And it lives between, so that's our resultant here, and it lives inside the gap here, okay? But when we're doing our graphical solution, the angle between our resultant here and the weight is going to be phi plus this angle here, okay? So you want to make sure, I'll just clean this up a bit, you want to make sure that not only do you calculate your phi, but you also take into account this, because we want this resultant R, okay, the angle between that and the weight, okay, when we do our graphical solution. So first thing you do if your graphical solution is you establish a scale, and I've decided that the scale is going to be 1 centimeter equals 100 newtons, because we've got 1,000 newtons. So we draw a weight force, and where does our weight force go? Our weight force is going straight down, vertically down, okay, so it's going to be 10 centimeters long, which makes it 1,000 newtons. That's pretty simple. Getting that bit is not a problem at all. Then you need to establish your pulling force. Your pulling force is going to be acting up from the horizontal, and you just extend the line through. You need to work out this angle here. Now the first time I did this question, I got an answer of 660 newtons. And the reason why I got 660 newtons was because I made this 20 degrees, because I looked at my free body diagram and I went, well, it's 20 degrees, but it's 20 degrees from the inclination of the ramp. So you have to add in, if you want to do from the horizontal, you have to add in this extra 15 degrees, okay, which is that ramp inclination. So that was my first mistake. So when I go 15 degrees plus the 20, I end up with 35. So that was the first thing that I needed to get right. Okay, so I do that and I just extend this line through. Okay, then I need to, that's going to be my pulling force that I'm trying to work out. Then I need to get my resultant in. Now we need to work out this angle here. And like I said, we worked out our angle of static friction, which was 21.8 degrees. So if I put 21.8 in here, that would be wrong, because between your reaction normal and the resultant of friction force and reaction normal is where that angle lives. But we want to get the angle between that resultant here and our weight. So we need to add in this 15 degrees as well. Okay, so you need to make sure that you get the angles right in these diagrams to get them correct. So I've gone here, I've written it's 15 degrees plus 21.8. So phi is 21.8, we worked that out, and the 15 degrees is a little bit extra because it's on an inclined plane. If it wasn't on an inclined plane, you'd just be able to use this value of phi. But because it's on an inclined plane, you have to take that into consideration as well. And we put that angle in, and then you can just extend a line down. So you use a protractor, and you would sit your protractor here, and you would make sure that that is 35 degrees, and then you sit your protractor up here, okay, and you make sure that you get that to 36.8. And when you do that, you will end up with a distance here of 6.2 centimeters. And we know that our scale is 1 centimeter equals 100 newtons. So the answer becomes 620 newtons approximately. Okay, so that works quite well. And when you do a free body diagram, if you're doing an analytical solution, you have to break down all your forces that are running up and down the ramp, okay, parallel to the ramp, and normal at 90 degrees to the ramp, okay. That's how to do this type of question. So I've done a free body diagram here, okay, and I've broken up my force P into its vertical and horizontal components. Vertical is P sine 20, horizontal is P cos 20. I've also broken up the weight force into its components. Going down into the plane is mg cos theta being the angle of the ramp, so I end up with 1000 cos 15, and down the ramp you always have to remember is mg sine theta, okay. So they're my forces perpendicular and parallel to the ramp, and then finally down the bottom here we have our friction force acting down the ramp and our reaction normal force acting up into the ramp. Okay, so I've broken it up into forces that are up and down the ramp and 90 degrees to the ramp. Okay, they're the forces you need to do this type of analytical solution. And then what I've done is I've gone all the forces parallel to the ramp when you add them up should equal to 0 because the system is in equilibrium. Anytime we have equilibrium, forces horizontal, vertical, and moments all equal 0. In this case, all the forces parallel to the ramp and normal to the ramp. Okay, so we end up here with 0 equals P cos 20 because at the moment we're doing parallel to the ramp. P cos 20 is this force here. And then we go minus 1000 sine 15, which is this force here going down the ramp, the weight force going down the ramp, minus our friction force, which is here. To the left is minus, to the right is positive. Okay? So, but we also know that friction force is equal to mu Rn, okay? Because we know that mu is equal to friction force over the reaction normal. Okay, so we end up with this force, this expression here. Friction force in terms of reaction normal is 0.4 times Rn. So we change the subject of this equation here that we had here by substituting in this expression for friction force, and we make reaction normal the subject of the equation. So that's our first equation that we need. Okay, reaction normal equals it should be P cos 20 minus 1000 sine 15 over 0.4. And then what we do is we substitute equation 1, which is this equation here, tick, tick, into our second equation, which is all the forces normal to the ramp. So we've got, what have we got normal to the ramp? We've got reaction normal is normal to the ramp. We've got mg cos theta, and we have P sine 20. Okay, in our free. So you look for all the forces. So P sine 20 is this force acting up here, and we've gone minus 1000 cos 15, which is this force acting down into the ramp, and then we've got plus Rn, which is our force reaction normal. So all of those forces, and we are then going to say to ourselves, well, we've got a variable here, Rn, we don't know, and P, which we don't know. Okay, we can't solve this if we've got two variables, but if we could express this reaction normal in terms of P, we'd only have one variable, and we can do that because equation 1, our reaction normal, is expressed in terms of the variable P. Okay, so we plug that into our spot here for reaction normal. So one is substituted in equation 2. When you do that substitution, it all simplifies down to that. 2.69p equals 1612.97, and when you do the calculation, it comes out to 620 newtons, which lo and behold is exactly the same solution as we got for our graphical solution. So I suggest what you do is do plenty of this type of question, remembering that you really need to understand how to create these free body diagrams with all the forces that are involved. Have a crack at it. Do plenty of study, and I will see you tomorrow. Hopefully it all goes well. Bye.